Good evening, everyone. In today's session, we are going to study some programs related to operators. So let us revise the bitwise operators. You must specify the operator or the symbol only once. That is, ampersand stands for bitwise AND, pipe is for bitwise OR, caret is for bitwise XOR, tilde is for ones complement or negation or inversion, you can say. This is left shifting, this is right shifting. So let us see the programs of shifting operator. So see here, every time when you shift a number, you can shift it by either one place or two places or three places or up to n places, either towards the left or towards the right. But suppose I say I want to shift the number 12 towards the left by 100 times. Okay, so each time we cannot manually shift the number 12 one by 100 times. Okay, so there's a particular formula in order to shift this and how to calculate what will be the resultant number. So that formula we'll be seeing today. See, if you want to shift a number, suppose I store a number 10 in the variable p. So I want to shift the number 12, which the number 10, which is stored in p, by one place. Okay, so as you already know, let me show you once again. Suppose you have the number 10, it can be written as by 8421. Okay, here we have 8 and here there is 2. So 8 into 10. Suppose I want to say the number 10 should be shifted towards the left by one place. Okay, this is the syntax. Your number, the operator, and by how many times you want to shift it. So by once, if I want to shift, this one will come this side, and one by one, the numbers move to the left, and you add 1 0 at the end. Okay, so this will become, here we have 8, here we have 4, and this is 16. So 16 plus 4, the number becomes 20. Now, if you have observed, 20 is nothing but 10 into 2. Okay, so from this, we understand that there is a particular pattern in the shifting. When you shift by once, you have to multiply that original number by 2. Okay, if you shift twice, you will multiply it by 4. Okay, so let us see how this formula is derived. So suppose you have the number which is 10, you shift it once to the left, then the formula is the number, say p, into 2 raised to 1. This 2 is common, raised to whatever the exponent, that will change. How? If you are shifting by one place, then it is 2 raised to 1. If you shift by two places, it is 2 raised to 2. If you shift by three places, 2 raised to 3. So shift by 4, then it is 2 raised to 4. Shift by 5, 2 raised to 5. Multiplying the original number each time. So 10 into 2 raised to 1, that is 10 into 2, that is 20. Now if I shift the number 10 twice towards the left, then it is 2 raised to 2 into 10. So it will become 10 into 2 raised to 2, that is 10 into 4, 40. Okay, so each time 10 into 2 raised to by how much you want to shift. Okay, this is, so by this we understand that it is a multiplication operation that actually gets done in the internals of your computer. Internally, what your compiler will do, it will multiply the number by how much you want to shift as a power of 2. Okay, 10 into 2 raised to by how much you want to shift. So as we can see, these are powers of 2. So this is nothing but first time you shift, then you have to multiply 2. Second time also you can shift. Again, if you multiply 2, third time you have shifted. Again, if you multiply 2, fourth time you have shifted. So it is nothing but multiply by 2 operation. So every time you shift towards the left, it is known as multiply by 2 operation. Okay, left shifting means multiplication. And it is obvious that it is multiplication because, as you saw, this was represented in 8421, but here I needed 16841, and so the number is increasing. Each time you go towards the left, the number will increase. Okay, I hope you realize this. So have you understood the formula for left shifting?
Yes.
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 Very good.
Yes,
Yes.
sir.
Yeah. So now when I say right shifting, what do you think? Should it be division?
Division.
Your decision.
Yes.
Yes,
Yes.
because we are
Yes.
going to reduce the number one by one. Okay. So let us see an example for this. I take the same number 10, which can be represented in binary as 1, 0, 1, 0. Okay, 8 and 2, that is 10. So 10, right shifting by 1. So this will come here, this will come here, this will come here, and this will come here. So I'll get what? This, and you must consider only this block. Okay, outside whatever goes, that is discarded. So the 0 has gone outside. What will come here now? 1. This 0 has come here, this 1 has come here. So whatever is inside this block is what you have to consider. If anything goes outside, it is discarded. But in left shifting, it was getting added at the end, right? Here we were adding something. This time it is getting discarded. So this is 4, 2, 1. It is 4 and 1, 5. Okay, 4 and 1 is 5. So this is equal to 5. If I shift 10 towards the right, it is 5. So I can say that 10 divided by 2 is 5. So this is divide by 2 operation. Let us see step by step. See here, this is right shifting by 1 means the formula is P divided by 2 raised to 1. P divided by 2 raised to how much you want to shift. That is 10 divided by 2 raised to 1. That is 5. That we have got it. If you shift towards the right by 2, P into 2 raised to 2. This 2 is coming from here. So 2 raised to 2 is 4. 10 divided by 4. Now 4 ones are 4, 4 twos are 8. Okay, so you have to take only the integer part. What I mean to say, suppose you have 10 and I'm dividing it by 4. Then you have to use 4 twos are 8. So you will get the remainder 2. Okay, you have to consider only this as your answer of right shifting. Okay, this is your this thing. You have to take only the integer part. If you want to continue division, what you do, you put a point, then bring down 0, then 4 5s are 20. So answer is 2.5. This you have to not do. As soon as it is not possible in integer division, you must stop. So where you'll stop? Up to this part. Okay, once you get a remainder, you must not take the point and bring down 0. Okay, you must stop here. Have you understood integer division?
Yes.
Yes.
Yeah, so that you must perform. Okay, most of the cases in programming we usually perform integer division only. So if I shift towards the right by 2, 2 raised to 2, 10 divided by 4 is 2. That's just now we got the quotient 2. Okay, when you do division you get quotient, when you use modulus you get remainder. Then 2 divided by 2 raised to 3, because I want to shift towards the right by 3. So 2 raised to 3 is 8. 10 divided by 8. 8 ones are 8. Okay, stop there. Now next what you'll do, P divided by 2 raised to 4, that is 16. Okay, so 10 divided by 16. Let me show you for simplicity what happens. 10 divided by 16. Now this is not perfect division. So 16 zeros are 0 and 10 minus 0 is 0. Okay, so quotient, this you must consider. Okay, so everything once you get 0, for higher values of the power of 2, again you'll keep getting 0. So at some point you'll keep getting 0 0 0. Okay, have you understood left shifting and right shifting using the formula?
Yes.
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 Okay,
Yes.
very good.
Yes.
and only integer division. You can remember that. Now let us see the negation operation, or you can say bitwise not operation. That is one's complement. Now this also has a particular formula, but can you tell me what is one's complement in your own words? Okay,
Zeros become 1 and 1 becomes 0.
yes, excellent, correct. So for example, again, if I consider 10, it is what? 8, 4, 2, 1. So the ones complement of 10, that is tilde 10 or negation 10. Each bit you must reverse. So 1 becomes 0, 0 becomes 1, 1 becomes 0, 0 becomes 1. And this is what? 4 and 1, that is 5. So not of 10, you can say not of 10 or bitwise not of 10 is equal to 5. So now the answer should be 5 at the output, but you will get minus 11 at the output. Okay, so why this happens, that we will see now in theory. You will not get 5 which is expected, you will get minus 11. So let us see why. So see here, if you have the number 5 in decimal, in binary it can be represented as 0 1 0 1. Okay, this is 4 plus 1, so 0 1 0 1. And now you have represented the decimal value 5 in binary. Now you have to take the complement, one's complement or negation, you can say, of that binary number 0 1 0 1. So when you reverse the number, or the reverse the bits of the number, it is nothing but you are taking the opposite of the bits. So you have 0 1 0 1, it will become 1 0 1 0. Okay, you have to simply take the 1 if it is 0 and take 0 if it is 1. So that is now what? One's complement of 5, that is not of 5. So in this case 1 0 1 0 is our expected answer. So according to 8421, 8 into 10. So 10 is my expected answer at the output. But this will not be the answer. What will be the answer is minus 6. Now why minus 6? I'll tell you all that. In computer memory, 10 is stored in the form of 2's complement. Okay. The number will be stored in the form of 2's complement. Now 2's complement, let me give you a simple example. So this is my 1's complement. Okay. This is 1's complement. If I want 2's complement, I have to simply add 1 over here. When I add 1 over here, I hope you know the rules of addition. 0 plus 0 is 0. 0 plus 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. Sum is 0, carry is 1. And 1 plus 1 plus 1 is sum is 1, carry is 1. So even if you don't understand this for now, it's okay. Just pay attention on what I'm showing you. You must add 1 to the last digit over here. Okay, this one. You must add 1 over here. So 1 plus 1 is 0 with the carry 1. 0 plus 1 is 1, 1, 0. Okay. Now, instead of doing all this and all, at the end, I'll show you one shortcut. So what is the decimal equivalent? 4 and 2, that is 6. Okay, so let us see our example. So you have got 1010. This is stored in the form of 2's complement in the computer memory. So to this 1010, I have to first take 1's complement, that is I get back the original. Okay, if I say this is my number 0101, if I take 1's complement, it is 1010. Again I take 1's complement 0101, means I'm getting back the original number if I take 1's complement twice. Okay, have you understood this?
Yes.
Yes.
Yeah. Yeah.
Yes.
Yes. So for this, you have got 1 0 1 0. You have to take one's complement of this. You'll get 0 1 0 1. And now you have to add 1 to this to get 2's complement. When you add 1, 1 plus 1 is 0 with carry 1. And then 1 plus 0 is 1. Then 1 plus 0 is 1. And 0 plus 0 is 0. Now, what is the 0 1 1 0? It is 6. And you should write it with a minus sign. Okay, so not 5 is minus 6. So the shortcut for this, instead of doing all this, is suppose you have the number 5, then not 5 is equal to, put a minus sign, and within brackets write the number plus 1. Okay, this is the shortcut. Suppose you have not 10, it is equal to, put minus sign, and within brackets number plus 1. Okay, so this becomes minus 6, which we have just now seen, and this becomes minus 11. Okay, have you understood the shortcut?
Yes.
Yes.
Yeah,
Yes.
yes. So let me show you the program example. See, int a equal to 10. This is initialization or declaration, can you tell me?
Both initialization.
Initialization. Both.
Yes,
Both
it is both,
initialization and
or
declaration.
yeah, yes, or it can be initial. Both is also correct. So I have done both. First, I have declared a, and then I have assigned some value to a. So it is both, you can say. Now here again there is initialization. So not 10. So what will be the answer of B? What will be stored in B?
Minus 11.
Minus
Yes,
Minus
11.
minus 11. Yeah. Okay. So let me comment this out. Means this will not come affect the output. You will not get error if you write anything like this. If it's in comments, if it is wrong syntax also. Okay. So you know the comments. So %d, I'm printing the value of B. So let me run my program. See here, not of 10 is minus 10 plus 1, that is minus 11. So this way for any number you can perform. Now see here, even with characters you can perform bitwise operation. So if I'm writing P bitwise within quotes, I'm writing a single character, that is capital A. So its ASCII value is 65 and the value of P is what here, 10. So 10 bitwise and 65. Okay, so represent 10 in binary, represent 65 in binary, perform bit level AND operation, and whatever is the result is in binary, convert it to decimal, and that decimal value will be the output at this output window. So with the characters, what will happen? Its ASCII value is considered. Here, logical AND. Okay. So ASCII value of A is 65, which is non-zero, so it is true. And P also has 10, which is true. So true and true, it is true. That is 1. Here, bitwise of ASCII value of A. So what will happen? A is what? ASCII value of capital A?
65.
Yeah.
65.
So
Minus
iska not
66.
operation. Yes, minus 66. Similarly, 65, you can shift it towards the left by 2. So the formula will be for this, you have to consider 65 in place of A into 2 raised to, 2 raised to what?
2.
2.
Yeah, yes. So 65 into 4, whatever the answer is, that will be this. So let us execute this program. Okay, so this left shifting, right shifting, we have already seen. Now, this is this one 0. Second is what? You're getting 1 because logical operation, both values are true. Then 65 is becoming minus 66, and left shifting 65 into 4 is 260. Okay, let me show you here. 65 into 4 is 260. Okay, so we have seen it with characters also. Now example set 2, you have a combination of operations that needs to be performed. Suppose A is 12 and B is 2. You can initialize multiple variables of the same type in a single line. A and B both are integers. On a single line, you can do by separating them with a comma. Now, A plus 1, right shift 3. So now you have two operators here. So which one you will evaluate first? That is decided by what?
Yes.
Next time if such things happen, I will remove the participant. If it's by mistake, I can understand, but don't do it on purpose. Now, see, I forgot what I was explaining now. Yeah, I was asking you the question that if you have a combination of operators,
Assignment operations.
if there is a combination of operators, then which one you will evaluate first? That how you'll decide? Okay, if it's by mistake, I can
Precedence.
understand the
Precedent.
yeah, precedence. Yes. Okay. Yeah. So according to our table, okay. So see here in our expression, we have this is an expression, okay. A combination of operators and operands is an expression. So first is binary operation. This plus is between two operands. It is binary, and this is what your right shifting. So you have binary plus and then right shift. According to the table, see here binary addition comes first, and after that what you'll do? Right shift, because whatever is I mean at the top of the table, that will be first, and whatever is below, that will be next. So first what you have to do, you have to add a plus 1. So a is 12, 12 plus 1 is 13, right shift by 3. You know the formula, right shifting means divide by 2 operation. 2 raised to 3, and what you have to shift the value? 13. So 13 divided by 8. Okay, so 8 2s are 16, so you have to take 8 1s are 8. So 13 minus 8, you get some remainder. Stop there only, quotient is 1. Okay, so this example 1 should give me the output 1. So let us run and see. Okay, so example set 2, example 1 we had considered, output is 1. Next, example 2. Here now you have parenthesis, and parenthesis has highest priority or precedence. Why? Because you can see here it is at the first level. So you have such questions in your assignment, so you can take a reference of what we are discussing now. So whatever is within parenthesis, you have to always read from left to right. Whatever is within parenthesis, execute it first. So a plus 1 is 12 plus 1, that is 13. Okay, so 13, right shift, and then this not 3. Okay, this is logical operator, and that has precedence after your parenthesis. So execute that next. So not 30, not 3. That is, in logical operation, 0 becomes 1, 1 becomes 0, or true becomes false, false becomes true. So 3 is a true value that will become false. So that is 0. So first addition, then logical not, and then right shifting according to your table. So if you have the table in front of you, it becomes very easy. So 13, right shift by 0. So it is nothing but 13 into 2 raised to 0. 2 raised to 0 is nothing but 1. So 13 into 1 is 13. So you're getting 13. Okay. Now,
Excuse me.
Right
It's
shift
yes.
table.
it has to be divided, no?
So it is
Oh,
right shift. Yes.
It has to
yes,
be
yes.
divided.
You have to divide it. So since it was 2 raised to 0, that is 1, even if you multiply or divide, it was giving same answer, but correct thing is to divide. Okay, right shifting means the value will decrease, so you must divide. Left shifting value increases, so you must multiply. So here it was the power of 0, so I was getting the same answer, but here division is the correct thing to be done. Okay, so good, you were alert when I was solving. Now left shifting, but negation and parenthesis. So first parenthesis is solved, a plus 1 is 13. Then what you'll do after that, look in your table, you have this tilde operator, that is your bitwise not operator. So if I write not 13, so this is bitwise operation, I've given you the shortcut. What will be the answer?
-14.
Plus
Yes,
14.
excellent.
0.
-4. Yeah. okay, minus 14, and left shift it by 2. Now, minus 14, how will it be represented in memory? You cannot say just like plus 14, how you do 8421 code, that is different. I've told you that negative numbers are represented in computer memory in the form of 2's complement. Okay. Negative numbers are represented in memory using 2's complement. So let us find the 2's complement of minus 14. Okay, so such questions are usually at the higher level questions, which you need to perform certain calculation manually. So for that, if you remember the rules, it's well and good. Otherwise, such questions are usually not asked. Okay, so just for curiosity, 14 you have to consider first, and it is by 8421 code 8 plus 4, 12, and 12, 13, 14. Yeah, so this is 14. Then you have to take its ones complement. So make zeros as ones, ones as zeros. This is ones complement. Then you have to add 1 to get 2's complement. Okay, this all will be taught to you when you study number systems. Okay, 1 plus 1 is 0 with carry 1. 0 plus 1 is 1, 0, 0. So this is 2's complement. And since I'm considering minus 14 ka 2's complement, what you have to do, there are two parts to represent this. In a block, consider two sections. You have to write the 2's complement of 14, and then you must write 1. So the total answer of 2's complement of minus 14 is 1, 0, 0, 1, 0. And this value you have to left shift by 2. Okay, so whatever answer you get, you can verify here. Similarly, you have to consider in the next example A, logical and minus 19. Both sides you have true. Okay, anything which is non-zero, maybe negative, maybe positive is true. So this will also give answer as 1. Now, again here what you have to do, minus 6. You have to consider bitwise AND. So you have to represent minus 6 in bits. Again, what you have to do, minus 6 is stored in computer memory in the form of 2's complement. So 6 is what? 0, 1, 1, 0. So this is 6. If I take ones of 6, it is equal to what? 1, 0, 0, 1. If I take twos of 6, the procedure is what? What I have to do?
Add 1.
Add 1.
Add
Yes,
1.
add 1. Yeah. 1 plus 1, 0, carry 1, 1, 0, 1. So this is twos of 6. So twos of minus 6 will be what? Just write 1 in front of it, isn't it? So 16, 8, and 2. 8 plus 2, 10, and 16, 26. So the binary equivalent of 2's complement of minus 6 is 26. So you have to consider 26 and A. A is what? A is 12. Okay, so 12 is what in 8421? 8 and 4. Okay, here all you have zeros. You have to take bitwise AND. So you'll get here 0, 1, 0, 0, 0. Okay, and this value is what? 8. Isn't it? Is this 8? Yes or no?
Yes.
Yeah.
Yes.
So this is 8. Yes. So let us see if we have got 8. Yes, we have got. Okay. So our calculations may be lengthy, but if you do them correctly, you'll get the correct answer. Okay. Similarly, you can try this one also at home. Then example 7 is a little big. In this, what you'll do, you have to first consider precedence because you have a combination of operators and operands. So you have bitwise logical binary addition. Then you have assignment operator. Okay, a plus equal to 1 is nothing but a is equal to a plus 1. Means you increase the value of a and store it in a. What I mean to say is If A is equal to 12, then I'm writing A is equal to A plus 1. That is 12 plus 1. That is 13. Okay. And if I write A plus equal to 1, it is same as I mean to say A is equal to A plus 1. Okay. This is the shortcut to write A is equal to A plus 1 is A plus equal to 1. If I write A plus equal to 10, then it is like writing A is equal to A plus 10. Okay, this is assignment operator. So whatever is in brackets is executed first. The value of A is 12. 12 is equal to 12 means A is equal to A plus 1 means A is equal to 12 plus 1 means A is equal to 13. 13 bitwise XOR 5. Okay, you have the number 13. It is nothing but 8, 4, 2, 1. This is 13. And you have got the value 5. So 5 is equal to 0, 1, 0, 1. Now bitwise XOR means A is true or B is true but not both, then the output is true. So XOR will be what? A is true or B is true but not both. So here you will get 0. Here also you will get 0. Here also you will get 0. Here you will get 1. Because A is true or B is true but both are not true. Only then you get 1. Here both are true, so 0. Both are false, 0. Both are true, 0. So this is 8. Okay, this whole thing is 8. So let me write here.
But in that operation, we have bitwise and also, no? So it has precedence more than bitwise XOR. So we have to perform that
Yeah, and
function
that
first,
yes,
I think.
that you have to perform. But since I've come to this point, so I was explaining how that operation occurs. Okay, yeah, this is
Okay,
you have
okay.
to perform first. This will come first. So actually, I got into explaining about XOR and all. So yeah, this you know XOR operation. So first you'll perform this, then whatever is in the bracket. After that, look into your table. Brackets you have performed. What else do you have? Bitwise and logical and binary addition. Okay, binary addition will come next, as you can see here. Okay, so in binary addition, b plus 1. So let me write the values below it. B plus 1 is 2 plus 1, that is 3. And bracket we have solved, we have got 13. We have got 13. Now, next we have bitwise, I guess. Uh, yeah, we have bitwise and only next. So in bitwise and you can perform in bitwise and A and B, 12 and 2. So 12, is equal to 1, 1, 0, 0. 12 and 2. 2 is equal to 8, 4, 2, 1. And operation at bitwise. So everything is 0 because same place you don't have 1. Okay, so you'll get 0 over here. Then you have in between OR operation. Then you have 0. Then you have OR. And here you have logical AND. So now you have logical and this was what you had 13 and here 5. So in our table, next what comes here? XOR, bitwise XOR. And we had got the answer 8. So let me replace this by 8. Now you have logical and logical OR. Which has higher precedence? Logical AND. After that, logical OR. So read left to right. 0, logical AND 3. What is the answer?
0.
0.
Yes, because yeah, one is false, so total is false. Then again read left to right. You have two ORs. These two ORs also have same precedence. So what you'll do? Associativity. Okay, so associativity based on the yeah, it is left to right in your table. So read from left to right what is coming first? This OR operation. So it is 0. Then you have this OR operation, which is 1. Okay, 0 or 8. 8 is what? True. So total is true. So you're getting 1 in example 7. Okay, as you can see. So this example 6 you can try at home. Okay, just take a screenshot if you want. I'm not asking you to tell me the answer, but you can try it at home. Okay, so now let us see the assignment number 3A. Okay, have you
While solving
understood
it,
today's
just show
session?
that
Next will be
binary session also in
if
the
it is
example.
asked in the theory exam. Yeah, in the theory exam, they may ask you such operations to test your manually solving skills. That time you have to show all this. But in your programs, if they are asking you to select the output from the multiple choice questions, if they tell you what is the output, then roughly you can solve. Okay, and then you can tick the answer. If in programs you can execute, in your practicals, there you don't have to solve all this, right? Okay, so now let us solve. Have you understood today's session? After this, now I'm solving assignment 3A. Any doubts up till now?
No.
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 We can use calculator
Okay.
over here, no? If you have to solve it quickly.
Yes, you can use. Yeah, you
Okay.
can use calculator.